attack that nobody knows about. And macro correlation also can help you discover zero-day attacks. And the reason this is important is that right now, you read about I don't know if any of you read Bug Tracks or the other Security Focus or the other sources on the internet that tell you about new vulnerabilities. But what the bad guys often do is hoard the vulnerabilities they find. Sometimes they try to sell them to the highest bidder. I don't know if you know, there was an attempt to sell a vulnerability in Vista for tens of thousands of dollars, and I heard the person was successful, believe it or not. And I don't think it went to Bill Gates. I'm just guessing. Anyway, in the case of zero-day attack, somebody launches you something that your intrusion detection system can't see very well, right? Because it's a brand new attack. Its signature library is not going to have that attack in the library. But the logic of macro correlation really doesn't depend on knowing about specific attack methods. Only things like patterns of connections between machines and the type of information that's exchanged. So event B could be a telnet connection, or it could be our login, or it could be secure shell. And the fact is that the same pattern, A leads to B leads to C, would still occur even though the specific nature of the kinds of protocols used and maybe the data that are sent between the different protocols would not be known. Macro correlation can also capitalize on vulnerability data. And here's what's really so important about this. Let's suppose we have an attack launched against, let's say, Linux Red Hat Enterprise 4.0 system, okay? So somebody's trying to attack, and there have been lots of bugs in GNOME and other programs within Linux, and so somebody has an attack, and they send that attack at that machine, but that machine's been patched. Well, how do you know the machine's been patched? You do a vulnerability scan, right? You're one of the good guys. And you find out that there's no vulnerability of, let's say, the latest GNOME format string problem or whatever the case might be. And so because of this, you can build a logic now that A leads to B, leads to C, and leads to D. And D means was vulnerable. It's a simple condition, was vulnerable. And if you have a vulnerability database that says, but this machine was not vulnerable, then you're in good shape because you don't have to sound an alarm. You don't have to get people going as far as incident response goes. This also lowers false alarms considerably. Well, I do automated data correlation for a living. That's my livelihood right now. And I'm telling you, if you want to do it, you have to consider four things. The first one is data transport. The second, you have to get the data to where they need to go. You need to normalize the data. That is, you have to parse the data so that you can understand what's what. Oh, this is an IP address. Oh, this is the name of the protocol. Oh, this is the name of the time that this event happened. And then you have to also reduce the data because there's way too much data coming in for you to be able to process it all. So somehow you've got to weed out the irrelevant data quickly, and you have to also do rule-based analysis of the data to find out what constitutes an attack, possibly a security breach. Now, I don't have time to get into this, but this is a model that was developed at the University of California at Santa Barbara by some students of Dick Kemmer, Professor Kemmer, and also this is out of the event correlation research that they were doing. And what they're saying is that you have to do things like normalization, pre-processing to filter out bad kind of data. You have to fuse alerts so that you don't send a separate alert for related events. Each related event, you have to verify that the alert is indeed a valid alert. You have to do thread reconstruction to determine whether or not you really have a series of events or whether you have one event, and so on down the line. I took this model, as well as a number of different things that have been done in event correlation, and built this. This is the basic model behind the appliance that my company sells. And I'm not here to get you to buy it or anything, although if a couple of you wanted to work for us, we'd just love to have you. Oh, by the way, we're 3 miles from Laguna Beach in Southern California. When I left yesterday, it was 85 degrees. When I came to Chicago and landed, I don't think it was above the teens. And I'm from Chicago originally, so I'm used to it. But I'm spoiled from living out there on the West Coast. But anyway, there's some weirdnesses, and no, they don't know what basketball is out there, so there's some downsides too. You know, those of you who are real Hoosiers know that you can tell when a new child's born because basketball hoop goes up over the garage. Anyway, the Hightower, you think I'm kidding, don't you? The Hightower model, what I have tried to do in this model is, on the basis of not only Kemmer's research, but others, come up with what I consider to be essential elements that you would need for event correlation. So notice that we need message collection from different data sources. When we get the data, we have to normalize the data and tag them so that we know what each individual piece of data is in case we have to do queries for that data at some later time. After we have normalized and tagged them, we have to parse the data. And some of you have learned through compiler theory about Lex and Yak and all that other stuff. And that's the same kind of thing we have to do here, only on a much lower level. And then we feed this to our rules engine, and then this goes written to a database system that manages a relational database. We also write to a flat database, and we have a user interface that interfaces with this. And there's some other components here that are lesser components, like the actual message generators, in case there is a successful attack. But constructing this model, which really works in real life because we QA test this product. We send attacks, just a huge number of attacks against this tool day and night. And our criterion is that it has 100% hit rate or correct rejection rate and a 0% false alarm rate. And we don't quit tinkering with this tool until we get results along that line. And human factors considerations are also hugely important, because it's great to know you get a message that tells you that there's a security breach, or you get a cell phone call that, somebody, let's say, text messages you or something. But it's also important to be able to do things like have a topological display where you can actually see where the event happened. And if you click on a particular device or a particular network to get detailed information, if you look at the lower left-hand corner, you might want to see something like memory utilization too. Because actually, in a real-time event correlation device, memory utilization turns out to be a major issue, as I will tell you really quickly. The major challenges are parsing outputs, because they use so many different outlets. Those of you who know about syslog knows that there are literally thousands of syslog formats out there. And unfortunately, when a vendor, like let's say Sun, comes out with a new release operating system, often they change a few things in the syslog format. The salvation for vendors will be syslog NG, but syslog NG is by no means, that's the next generation of syslog. It's not universally accepted. You have to, for data analysis, one of the huge challenges is find out what really is worth analyzing, what isn't, what kind of data are you going to store in each database that you have. When you have a piece of a rule, logic, condition fulfilled, you open something we call a thread. Those of you who've had operating systems know what threads are there. These are application threads. And now the question is then, how long does your thread stay open? Because the longer the thread stays open looking for more information, the more memory consumption there is. But if you close the thread off quickly, let's say 15 seconds, because no other related event comes in, then you're going to miss slow and gradual attacks. And some attackers do launch slow and gradual attacks. Also, how long should new data be appended to any single incident? It's the same kind of problem. The longer you wait, the not only more information there is with every incident, but the more memory consumption you have. Resource consumption is always a problem. It's usually memory. We've got great hardware. We don't really have problem with CPU utilization, but we do fight memory management problems from time to time. And also, do you want to put an intrusion detection server on the machine that's actually doing the event correlation? And I say, heck no. Heck no. Leave those cycles for something else. Let some other device process the intrusion detection data and send it to you. Don't reinvent the wheel on your event correlator machine. You have to worry about integrating vulnerability scans, especially if you have more than one vulnerability scanner. And also the question is, how can you really create great macro correlation rules? It's not easy. It sometimes takes a long time. Some of the rules that I have thought of have taken a month or two to actually refine to the point where I think they're finally usable in the product. And if the quality assurance people test it and it doesn't reveal the results we want, then I have to go back to the drawing board. So in conclusion, we used to just talk about intrusion detection. But lately, intrusion detection event correlation has been surfacing as an increasingly important topic. And it's becoming to the point where intrusion detection and intrusion detection event correlation are merging into one